Okay, I'll try this one again. I had recorded it earlier, but it's difficult to make out because I was in the recovering room and couldn't talk very loud, and there was a lot of noises in the background. So this one has to do with mainly tides, which are the last of the different types of waves that we'll be talking about. So tides are periodic short-term changes in the height of the ocean at a particular place. They are, as we learned in chapter 10, they're caused by a combination of gravitational forces of the moon and the sun and the rotation of the earth, so where it's positioned at a given time. The wavelength of tide waves can equal half the Earth's circumference, so it is a shallow water wave. It can never be a deep water wave because, if you remember, deep water waves are called that because they are more than half their wavelength deep. So that's just not possible on the Earth. The deepest part around the Earth, again, is 11 kilometers, so it's just not possible. So they're always feeling the pull of the ocean floor underneath. They are, my cursor, there we go. They're the longest of all waves. Their wavelengths half their circumference of the Earth, so that's pretty long. So longest of all waves. And because they're so big, we tend to probably not even think of them as being a wave. There's a few theories out there of how tides are formed. We'll be focusing on two, the equilibrium theory and dynamic theory. You should be able to briefly explain them or understand what they are. Sorry. So, equilibrium theory basically is the one that talks about how the gravitational attraction of the moon and the sun and the Earth's rotation kind of work together in making the tides. So the combination of forces of the gravitational pulls and then the inertia, the centrifugal forces of inertia opposite those gravitational pulls causes the tides to be higher in certain areas and lower in others. So the result, if you look up here, here's showing the pull due to the gravity of the moon, and then equal and opposite that on the other side is the bulge due to the centrifugal forces of inertia. So the bottom graphic shows how large, I guess you could say, how strong of a pull you get from the moon as opposed to the sun. Okay, so because the moon is closer, it's the gravity due to the moon has a greater effect on the tides and where they're high and low than the effect of the sun. But it's actually a combination of the two that tells just how high the tides are and in what area. So the location of the high tides and low tides are going to be determined by the position of the moon, mainly because it has the stronger effect of the two. Okay, so there's a video there that you can watch, and that'll help to see it in more of an animated view, so it can help you understand better. The second theory is the dynamic theory, and it's basically a mathematical approach. It includes the responses of the ocean to the shape of different ocean basins, and the approach treats tides as long waves. So, mathematical approach where the tidal observations are analyzed mathematically, and it allows them to make predictions, and that's how they come up with the tide tables, tidal charts and tidal tables that we can see There's lots of them online, but they're referred to a lot by people who spend a lot of time at sea, fishermen, naval people, even surfers and swimmers who want to find out when high tide's going to be, or maybe you like to be at the beach at low tide, so you probably want to read the tide tables, or be able to help. Alright, so we're going to take a little closer look at how you read a tide table, but in order to understand how you read them, you need to understand or why it is that there's a difference in when the tide is each day. We need to understand what they mean by a tidal day. So, again, the tides depend on the position, more on the position of the moon as it's going around the Earth. So, our watches are set by a solar day. A solar day, basically, if you were at this position on the Earth, okay, and you were looking up at the sun, and the solar day is basically for the sun to get back in that same position above, meaning as the Earth rotates. Okay, how long does it take for it to rotate for the sun to be back in that same position? It's 24 hours. Okay, now if we watched the moon from that point as the Earth rotated, and we got to 24 hours, which is a solar day, the moon wouldn't be in the same position above us. It wouldn't get back to that same position. In fact, the Earth has to rotate an extra 50 minutes in order for the moon to be in that same position above. Okay, so we call that a lunar day. So it has to take an extra about 50 minutes in order to get back to that same position. So a solar day is 24 hours, and a lunar day is about 51 or so minutes longer. So 24 hours and 51 minutes. So if you were reading tidal table, this one, they come in different formats, but if I were looking at this one, the tidal chart for January 4th, for last year, okay, these heights are based on the height above the average low-level water level. Okay, so the lower numbers means it's not very much higher than the average low-level water level, so that would be the low tides. The higher numbers are when it's obviously much higher above the low-level water level, so those would be the high tides. So it says, what times are high tides on January 4th? So look for the larger or higher heights. So 0.9 meters or 3 feet above the average low level. It's at 7:38 in the morning. And then again at 7:12 at night, there's another high tide, 1.4 meters. And this would be the higher high tide. Okay, so this is the lower high tide, and this is the higher high tide. So if we look then, it says how much later is the high tide on the second day? Okay, so if we look on the second day, it's at 8:23 in the morning and at 8:04 at night. So it's about 51, give or take a couple minutes, depending on where they're at. It's about 51 minutes later the next day. Okay, spring and neap tides. So spring tides are basically when we have our highest high tides and lowest low tides. And it doesn't necessarily mean it's just happening in the spring. They're called that, and they actually happen during new moons and full moons. Because during the new moon or the full moon, the moon is directly in line with the sun and the earth. So the sun's pull on the water around the Earth, on the ocean, adds to the pull from the moon. Okay, and if it's on the other side, then it adds to that centrifugal force due to inertia. Okay, so that when they add together, then obviously the tide's going to be really high or really low. So this is where the higher high tide is, and then along here, where the water's pulled so far away from the Earth, then this would be where the low tides, the lowest low tides would be. Okay, and the neap tides happen when, if you drew a line from the sun to the middle of the Earth and the moon to the middle of the Earth, and you can see that they meet at a 90-degree angle. So they are the poles that they have on the ocean are exactly, they're the greatest they can be against each other. Okay, so because the pull from the sun is pulling water away from, where did my cursor go? There we go. Because the pull of the sun is pulling some water away from what's being pulled towards the moon, or due to centrifugal forces, it diminishes or makes it less high. Okay, so during the neap tides, it's actually when the difference between the high and the low tides is at its lowest. Okay, so that's when they have the lowest high tides, so it pulled the high tides as much as it can, so they're lower, the lowest high tides, and the highest low tides. Okay, so that is when we have neap tides. So that is during the first quarter and third quarter moons. New moon and full moon is when we have spring tides. Okay, first quarter and third quarter is when we have neap tides. Again, there's good videos and animations there for you to see. Now, the tidal patterns that you'd see in different regions fall into really three main categories. The first is diurnal tides, and diurnal tides, if this is a 24-hour period, then you only experience one high tide and one low tide, because then you get back to normal spot. Okay, so one high tide and one low tide per day. If it's semi-diurnal, then you can see there's 2 high tides and 2 low tides. So, and not only do they have 2 of each in the day, but they're at the same levels. Okay, so 2 high tides are the same level, and the 2 low tides are the same water level. A semi-diurnal mixed tide means that there's 2 high tides and 2 low tides during the day, but they're mixed levels. So there's a higher high tide and a lower high tide, and then there's a higher low tide and lower low tide. Okay, they're not the same water levels. Around here, we have a mixed diurnal, so semi-diurnal mixed tide. So we have 2 a day, but they're not the same water level. So 2 of each a day, not the same. This is kind of a neat graphic. It shows where the different tidal patterns are experienced in North and South America. So the red shows semi-diurnal tidal patterns where they have 2 highs and 2 lows a day, but they're the same levels. Okay, the diurnal, so that's 1 high and 1 low a day, are shown in green, so they're around the Gulf of Mexico. It's really the only area that's showing it that way. Okay, so they have 1 high and 1 low tide a day. And then the semi-diurnal mixed, where they have 2 highs and 2 lows, but of different levels, that's all the blue. Okay, so all the blue areas have like what we do. Now, it doesn't mean that they have the same level, but they have the same kind of tidal pattern. Now, we're going to talk about a few other properties of tides. Oh, excuse me. First of them is amphidromic points. Okay, so basically amphidromic points are no tide points in an ocean that are caused by basin resonance, friction, the Coriolis effect, which kind of tends to make things move a certain curved appearance, and other factors around which tide crests will rotate. There's approximately 12 amphidromic points that exist in the world ocean, and they're sometimes called a node because at that point there is no tide, so it doesn't rise or fall. There's a small node that's in the Gulf of St. Lawrence, and that can affect our tides around here. So this is showing a number of the amphidromic points in the world ocean, and you can see them at the joining point of the tidal crests. So these are showing the patterns of the tidal crests, but you can see at the kind of center of each, that is where there'd be a no tide point or an amphidromic point. Okay, so tidal crests move in a counterclockwise pattern around the basins of the northern hemisphere. Again, Coriolis effect comes in big time here. The resulting circulation, they'll often call an amphidromic system. So when they look at them, all the points overall and how they affect each other. And we're not going to get into it in a lot of detail, just to understand that they're points of no tide. Okay, and this is another diagram showing them. There's approximately 12 of them. Seems to be stuck. Okay, I'm not sure why, but PowerPoint froze up there, so just paused and restarted. So we had just finished talking about amphidromic points, and basically, as long as you understand that they're points of no tide, and there's approximately 12 of them in the world oceans, and they're points of no tide around which the crests will rotate. Okay, so purple, you see the purple ones, then the rotation around them is in a clockwise direction on here, and the rotation around the green ones are counterclockwise. So most of the green ones are in the northern hemisphere, and most of the purple ones are in the southern. That's to do with the Coriolis effect, which way that they're rotating. Okay, a little more properties of tides and tide levels. These are just terms that they use to describe tide levels. So obviously high water is the greatest height that the tide reaches in a day, and low water is the lowest level it reaches in a day. Mixed tide systems like ours have 4 of unequal strength. So again, we have a higher high tide and a lower high tide, a higher low tide and a lower low tide. The mean tide is just when they use a calculation, so it's calculated by taking the average of all changes in water level over several years. Flood tide is basically the tide when the tide is rising or coming into an area, and then ebb tide is when it's falling or going out from an area. Okay? And I think the animation is about ebb tides and flood tides. Tides in a confined basin. So the range of high and low tides varies across different topography that they come across around the Earth, and they certainly vary within different ocean basins. So the largest occur at the edges, especially in bays and inlets, where the energy is concentrated in a smaller area. A mini amphidromic system develops within those types of areas, and that's why we end up with extreme tides, like what we see over in the Bay of Fundy. So some of you may not have seen them before, but in that area there's a natural oscillation, meaning movement of the tide vertically up and down, natural oscillation periods of 12 or 24 hours, and the tide can rise and fall 15 meters. So you really have to watch when the tide is going to be rising and falling, because you could get caught out there and not be able to get to safety in time. So just if you're over there, make sure you pay attention to the times. I think this one shows a video too, so if I get to click on the picture, and it will show you a video of the tides. I think it's a time-lapse video of them. Tidal bore. I can remember growing up and going over to visit relatives in Moncton, and always hearing about this tidal bore, and I never saw it because anytime we'd be driving by the area where I'd see it, it wasn't coming in until about 5 years ago, I think. And I was expecting this great big rush of water, really high, just by how people described it, that it would be awesome to see. But where I was, the tidal bore was actually, it just looked like a little trickle of water, like a small wave, a tiny wave, making its way along the riverbed. So it almost looked like there was no water there, and then this trickle of wave would come in, and it was not overly fast either. So the tidal bore is a high, often breaking wave generated by a tide crest. It advances rapidly up an estuary or river, and so to me as an observer, it didn't look overly fast, but in wave terms, it was relatively fast. It occurs in inlets and some rivers exposed to great tidal fluctuations. It's a true tidal wave, but it's usually not very destructive, and they're fairly predictable. Tidal currents are mass flow of water induced by the raising or lowering of sea level, owing to passage of crests or troughs, the tides. So an ebb current, just we talked about ebb is water rushing out of an enclosed harbor or bay because of the fall in sea level as a tide trough approaches. So as a trough is approaching, it kind of pulls water outward. Okay, so it's leaving a harbor or bay, so that's a major current that's forming from the pull as the trough is approaching. Flood current is when water is rushing into the enclosed harbor or bay because there's a crest approaching. Slack water occurs at the time when the tide slows and it's kind of reversing itself. So that one is kind of a different term that you haven't seen before, and you probably should make note of that one. So ebb is when an ebb current is when it's been pulled out. flood current is when the crest is moving in, and then the slack water occurs when the tide slows and is reversed, going the other way. In terms of tides and the organisms, we've seen this term before, so it shouldn't be new. I just wanted to remind you of it. So there is an intertidal zone. Again, that's the area where the land and the sea meet. Oops, sorry. Between the high and low tides. Okay, so in here, between the high and low tides, where the water goes up to at high tide and where it's up to low tide, in between there, that's the intertidal zone. And the organisms that live there, they have to be adapted to huge changes in moisture, temperature, turbulence, and salinity, because for part of the time they're covered with water that's moving over them, and then for part of it they're exposed to the air. So they have a lot of neat adaptations to be able to survive those major changes. There is a cool little video that shows the grunions. So I guess that maybe I could have shown some of them. Let's see if this one will work. Well, I guess you can watch it on your own. Again, the internet's not working, so these are a type of fish that spawn from late February to early September. But the neat thing is they swim ashore at night after the highest spring tides, and you'll see them, hundreds of thousands of them, laying eggs in the sand. And then the eggs won't hatch until that following spring tide. Okay, so it's neat because you see them, all these fish laying on the sand, laying their eggs, and then the eggs don't hatch until that following spring tide. So, pretty neat. So if you watch the videos or Google them, it's kind of neat to watch because there's so many. I think that is it. Yeah. It's just another graphic showing the intertidal zone and the kind of organisms that you find there. It's rather fuzzy. So again, if you have any questions, please watch the little videos and animations because they'll help you to understand things better. If you're watching this video, pause and take the time to watch the animations or videos, or go back and re-watch things that you're not sure about. Ask each other questions, and don't be scared to ask me questions. I know as a whole, as a group, you're reluctant to ask many questions, but I hope that as you're getting ready for your exam or trying to work on your test assignment, that if you have questions that you'll not be too scared to ask. So send me an email, an Edmodo message, or ask me in person. But please ask. I'd love to help. Good luck as you get ready for your exams.